In the last lesson, we left off with Lucy, a nice example of a transitional species from ape to human. And Lucy was bipedal and had lots of skeletal features that we will see in the later human lineages. Let's pick up the story with hands. On the left here, we see the chimp hand and then the human hand. In chimps, the thumb is a small digit, and they use powerful fingers as hooks to hold on to branches. In humans, the thumb is larger, stronger, and opposable to the other fingers. So in our hands, we can touch the thumb to the tips of each of the fingers here. Humans also have a tendon that allows the last joint of the thumb to flex, unlike chimps. In addition, the digits are less robust, and that provides for greater dexterity of our hands. And down here we see the tips of the human fingers are wider, increasing the surface for manipulating objects. So let's examine the chimp hand. First, we remember that the chimps are knuckle walkers, so they use the middle here, as we see here on the left, the middle fingers as support. And if you look at those fingers, there's a tough pad on the back of the fingers where it contacts the ground. As we see on the left here, chimps have long fingers and short thumbs that are well suited to climbing trees and hanging on branches. However, the long fingers and short and weak thumbs make precision grips difficult and weak. Consider the hand over here on the right. Look at the thumb of the chimp. Now notice it is making contact with this digit here, but the chimps have difficulty sort of touching the tips of all of their fingers. And down here, look at how it holds a little stick. Now, if that were a tool, it just doesn't have the kind of grip on that tool that a human hand can make. And so in the human hand, we can form precision grips with strength, as needed when using a tool held with the thumb and fingers. And this was the situation facing our ancestor Homo habilis. You'll recall Homo habilis used its brain to find and make stone cutting tools, but of course it had to use the tool with its hands. As we see here, a person using a sharp rock flake to scrape the meat from a bone. So the idea is natural selection then would favor any modifications of the hand that made tool use more effective. Why? Because more effective tool use gets you more meat, and that would be a survival advantage. So natural selection favored a larger and more robust and a stronger thumb in the human hand. Now that brings us to a very important ancestor who lived 1.8, 1.5 million years ago, and that's Homo erectus. And this is a famous fossil Turkana boy. And you can see there were lots of bones found in this specimen. And you might notice that it's much closer to a modern skeleton. It's got a more modern shoulder and wrist and thumb and fingers. It's got a more modern rib cage. It's got smaller teeth, jaws, and small intestines, and it's got skeletal features for long distance running. And this species also is associated with a more sophisticated tool called a hand axe. So Homo erectus had a shoulder joint that is more suitable for throwing. By contrast, the ape shoulder is better for hanging and manipulating around in the trees, but this is a shoulder that will allow human descendants to be able to throw accurately. And the value of accurate throwing would be a selection pressure for the evolution of a throwing anatomy. Humans are one of the few species on planet Earth that have really accurate throwing abilities. And this would come in really handy if you're defending a carcass from potential predators or other competing scavengers. Another feature in erectus that we also find in modern humans are the long legs. Long legs are a running adaptation. So long legs helped erectus run down prey. The large gluteus maximus muscle is also an adaptation for running. In addition, the Achilles tendon helps push off during running and jumping. So many prey animals easily overheat when pursued persistently over long distances. They have limited body cooling systems, not adapted to prolonged exertion. So Homo erectus could take advantage of this. If they could outrun, in a sense, if they could just keep on running after these prey species, they would be rewarded. A prolonged chase would be rewarded with an exhausted animal collapsing to become food for an Erectus family. Modern hunter-gatherers still engage in long-distance persistence hunting. And the advantage of long-distance persistence hunting would set up selection pressures for better cooling systems in the human body. And so now we're going to see the evolution of a new trait that is not found in our ape cousins. Increased sweating evolved to cool the body. Homo erectus was hunting during the day, in the hot part of the day, and this cooling system allowed them to hunt during the hot part of the day. By the way, that's also when a lot of the predators are sleeping, so this was a safer time to do your hunting. The fluid part of sweat comes from the interstitial fluid, that's the fluid between cells, which ultimately comes from the fluid in the blood. Eccrine sweat glands produce the sweat that is released through pores. When sweat evaporates from the surface of the skin, it takes heat away from the body, thereby cooling the body. Let's take a look on the right here. Here is the eccrine sweat gland, and so the fluid will rise up to the pore here, and when the sweat evaporates from the surface of the skin, it has the effect of cooling the skin. Now, these eccrine sweat glands are found all over the skin's surface, but they are concentrated in certain locations in most mammals. So in chimps, like most mammals, the maximum density of sweat glands occurs on the feet and the hands, and that serves to enhance the grip when you're kind of moving around in the trees. The head also has a higher concentration of sweat glands. But in humans, they have a greater concentration of these sweat glands all over the surface of the skin. And this diagram will show us the difference. So on the left, we have the chimp with limited sweating capacity on the surface of its body. So here's one eccrine sweat gland here. There's a different sweat gland called the apocrine sweat gland. That's for a different purpose. But so notice the chimp then, it's got a low density of sweat glands on its body surface, whereas in humans we have a high density. So all of these would be pores connected to sweat glands, and so we can cool the surface of our skin to a much greater degree than the chimps. So increased sweating is an adaptation. Humans have about 10 times the density of eccrine sweat glands as chimps. In hot African climates, human ancestors evolved more sweat glands as an adaptation to permit activity during the hot part of the day, when a lot of the predators were resting. Let's also use this diagram to illustrate another evolutionary change. On the left, we see the hair that covers the surface of the chimp body, and humans have hair as well, but there's a notable difference. When hair is really thick, we call it fur. So in the evolution of the human characteristic, there's just a loss of fur. So humans and chimps have about the same density of hair follicles, but human hair is much finer. So the loss of fur is thought to be an adaptation to enhance the cooling efficiency of sweating. So the loss of fur would be another adaptation for hunting during the day. Now, humans did not become hairless, but more accurately furless. Vellus hairs all over the body allow for the efficient evaporation of sweat. So again, the density of hair follicles is similar in chimps. We just have very fine hair over large portions of our skin surface. All right, so let's do a little recap here. Our Homo erectus ancestors were becoming very mobile ancestors. Competent hunters as well. We, like Turconaboy, can run longer distances than many prey species, and again, modern hunter-gatherers continue to use the persistence hunting. We have several anatomical features that are adaptations for running. Long legs, springy feet, an Achilles tendon, large gluteus maximus muscles. We can run in hot conditions if water is available. And of course, the loss of fur and increased sweating kept our bodies cooler. But in addition, scientists think that around this time there may have been the introduction of new cultural artifacts like objects to carry water, and that would have made this persistence hunting strategy even more effective. These adaptations allowed humans to plan longer trips, carrying water and plotting courses near known water sources. Importantly then, for Homo erectus, longer migrations were now possible. You see, the chimps are restricted to the forest. They're just not well suited for leaving the forest into different kinds of grassland habitats over any long amount of distance. So they're restricted to their forest environment. But not so for erectus. Homo erectus had a set of adaptations now that it would allow it to run right out of Africa. So moving around into different environments triggered new cultural innovations. So as Homo erectus then spread around into different kinds of habitats, well, that would have then triggered them to figure out new ways of doing things in these different habitats. And so cultural knowledge would begin to accumulate. We're starting to see the takeoff of the cultural way of life for our human ancestors. Let's consider one more physical change that we see in modern humans relative to our ape cousins. And this it reveals that in our past there is evidence of food struggles. Now, food scarcity or variability, something we talked about in a previous lesson, that is a feature of living in a grassland habitat. There's more seasonal variability for food. Well, that would be a selection pressure for the ability to store calories when you had enough food, and that's what fat does. So greater fat tissue to store calories. So under conditions of food scarcity, evolution is going to favor mechanisms to store calories when they're in abundance, so that when you're having a hard time finding food, you can tap into your fat reserves. Fat adaptations likely emerged after the move out of the forests. And again, because in the grassland habitats, you're more likely to have scarcity during the dry season. Now, humans have special fat storage sites, and they may differ a little bit between men and women. We have a fatty layer under the skin that makes our skin more cushiony than other mammals. And the only other mammals with similar fat to humans is whales. We can see our fattiness with the little ones here, the little babies. Human babies have 4 times as much fat as other mammals. Infants are fat as a buffer to keep building their brains even during scarcity. 85% of their energy is used to build their brains. Whereas when chimps are born, pretty much most of their brain development has already happened. Now, women can function well with 33% of body mass in fat. In modern hunter-gatherers, they range from 19 to 24% fat. But if fat is reduced too much, below approximately 20%, then ovulation and menstruation stop, as the reduced fat reserves would jeopardize fetal development. So this shows the key relationship between fat storage and supporting the development of babies and their brains. Take a look at this chimp. This chimp happens to have a condition where it's hairless. Forests don't have overabundance, but chimps can always find something to eat, so storing fat for lean times is not necessary. Chimps and bonobos' bodies are very lean, about 1% fat. Of course, extra fat would be a burden when climbing trees. So again, there's no selection pressure for the evolution of fat deposits in these forest creatures because food is readily available. So they're not going through the kind of seasonal scarcity that our ancestors faced. So in this lesson, then, we've seen several examples of how natural selection could modify the ape anatomy to become more human.